Alright, so we're basically learning more inequalities. This next one's a pretty famous one. They seem to come up a lot in homework problems, whether they're in our class or in calculus class or wherever the case might be. But they're basically our double angle formulas. And so essentially the argument, the angle that's being the sine's taken of, or the tangent or the cosine, is we're basically doubling it up. So rather than just a singular angle, we have a double angle. And it turns out that the sine of a double angle is 2 sine of the angle and cosine of the angle. The tangent of the double angle is 2 tangent of the angle, 1 minus over the tangent squared. And then the cosine actually has 3 different versions. So these actually are pretty easy to prove. So let me go ahead and I'll go ahead, rather than playing around with them and showing you the video, I'll go ahead and I'll prove these ones because we basically just use our sum identities to get the job done with regard to these functions. So in the first one, the sine of 2a, right, we can rewrite this as the sine of a plus a, and then when we go look at our sum angles for that, we basically have that breaks up into basically the cosine of a, the sine of a plus, right, and what we end up having there is the cosine of a, the sine of a. Alright, so that's basically how that breaks up. And so what we basically see is we have the cosine and the sine twice. So we have, just to kind of mirror that, multiplication is commutative, so we get the sine of a cosine of a. So that, pretty easy to prove. Very, very easy. Okay. The tangent is also very easy to prove. If we look at the tangent of 2a, well, we can rewrite that as the tangent of a plus a, right, with regards to that. And of course, once we have it written in that way, we can basically invoke our trig identity. And for the tangent of a sum, right, this is basically tangent of a plus the tangent of a all over 1 minus the tangent of a times the tangent of a. And of course up here, tangent plus tangent of the same argument, we have 2 tangent of a, and then down here below, what we basically have is tangent squared. So 1 minus the tangent squared of a. So that one, again, pretty easy to prove. And then last but not least, the wild card is the cosine. There's actually 3 different versions, which makes it a little bit tougher to use, but it's pretty easy to prove all those. Kind of keep in mind when we do this, we know that cosine of a plus the sine squared of a is equal to 1. So that's our Pythagorean identity. And this basically is the go-between. And I actually think in some previous videos, in your homework, and I even think on the test, I made you guys prove at least one of these, if not once. So we've kind of seen them already. But again, cosine of 2a, let me write that better. The cosine of 2a, we can rewrite that as the cosine of a plus a. And once we have it written that way, using the cosine of the sum, this is the cosine of a minus the sine of a sine of a. And so this is basically your cosine squared of a minus your sine squared of a. So we've basically proven the first way to write the cosine of a double angle. And now it's basically, what do you want to rewrite? So if I rewrite this, if we replace this cosine, we can rewrite that as 1 minus sine squared a, and then minus the sine squared a. And so we have 1 minus 2 sine squared a. So we've just basically proven the second one. To prove the third one, let me go back to this. Cosine squared a minus sine squared a. What I'll do is rewrite that with the Pythagorean identity. So we have a cosine squared a minus, this becomes 1 minus cosine squared A. And if we distribute the minus, we get cosine squared A minus 1 plus cosine squared A. Cosine and cosine, there's your 2 cosine squared A minus 1. So we've just proven the third one. So there's basically algebra behind that. It's essentially we're applying the sine of a sum to get this identity, the tangent of a sum to get that one, and then we're applying the cosine of a sum to get the first one, and then we just play around with our Pythagorean identity to get the other two. Alright, so that basically is our proof for those. And now what we're going to do is basically do what we have been doing with identities, is we use them to find exact values of situations, we use them to rewrite and simplify expressions, and we use them to prove identities. So that's what you'll be seeing in the next videos coming up shortly. Same rhyme and reason, if you would, but with just new identities to work with. See you guys in some videos coming soon.